Hello, everyone. Thank you for joining in. My name is Ruchit Agrawal, and I am a doctoral candidate in computer science at the Queen Mary University of London. This work has been carried out jointly with Daniel Wolff from ICANN Paris and Simon Dixon from Queen Mary University of London as well. Our paper is titled Structure-Aware Audio-to-Score Alignment Using Progressively Dilated Convolutional Neural Networks. And I would like to thank the European Union for funding this research under the MIP Frontiers program. So without further ado, let's get started. So I'd like to begin with a brief introduction of the task at hand, that is audio-to-score alignment. Generally speaking, alignment of any kind aims at mapping the matching positions or indices in multiple streams of sequential data. The streams could be multimodal, such as video and text, or audio and video, or audio and text, such as speech-to-text alignment or subtitle alignment. Well, in this case, we are working on classical music performance, with the streams being the audio corresponding to the performance and the sheet music corresponding to the score. So now, given these two input sequences, our goal is to map all the matching positions between the two sequences. So traditionally, audio-to-score alignment is performed using dynamic time warping or hidden Markov model-based approaches. Dynamic time warping is basically a dynamic programming method which measures the similarity between two temporal sequences and then generates an alignment path by warping the two signals according to this similarity. So the equation is generally given like this, where for each point we calculate the total cost to be minimized so far as the cost at that point, and also the minimum cost so far. So it's a dynamic programming method. And similarly, HMM is a statistical Markov model in which, given an observable output sequence, given by the y's here, our goal is to determine the transition and the emission probabilities for the unobservable hidden states, which are given by x's here. So far, so good. But here's the catch. In the alignment setting, both these methods typically assume that the musician follows the score from the beginning to the end without inducing any structural modifications, which is often not the case in real-world scenarios. In real world, the repeats and jumps are an integral part of classical music performance. Take a look at this example. This is how it's supposed to be played in theory, but in general, a performer might choose to add a few repeats or even skip a few repeats, especially in the practice setting. So as seen on the right, the computation for DTW and HMM-based models constrain the alignments to progress monotonically through the score and are thereby unable to model structural deviations. This is the example of the DTW, where the alignment increases monotonically without jumps. And this is the Markov assumption or the Markov property. It states that given the present state, the future only depends on that state and not on the past states leading so far. So a few approaches have been proposed to mitigate this issue, namely jump DTW for audio-to-score alignment and Needleman-Wunsch time warping for audio-to-audio alignment. So the first mod, jump DTW, is an extension of DTW, which allows for some jumps between blocks, basically. And this method identifies the block sequence taken by a performer along the score, based on a priori jump locations. And Needleman-Wunsch time warping is again a pure dynamic programming method with an added weighting mechanism. So we'll talk about the limitations of these approaches. So jump DTW, first of all, it relies on an OMR system to predict the block boundaries, and it needs these boundaries to be further manually corrected further, so as to be accurate at the frame level. So basically, it is unable to model the deviations that are not foreseeable from the score. And even for those which are marked in the score, OMR doesn't always detect them. For Needleman-Wunsch time warping algorithm, one caveat is that it doesn't align repeated segments or repeated phrases. So for example, in this case, there is a repeat after this point. But what ideally it should do is, ideally it should jump back and then continue the alignment. But what Needleman-Wunsch time warping does, it waits until the two sequences start matching again. So this makes it incapable of modeling repeated phrases. And especially in the practice scenario where multiple deviations and interruptions are possible, this is not really applicable. So these are challenging to model using rule-based approaches. And machine learning methods offer promise at effectively addressing these challenges. Well, we mentioned machine learning, we need data. Well, there's a lack of data with fine-grained annotations. That is, measure level annotations are not available in most data sets. So we require a method that can work without a priori jump locations. So we propose a custom CNN-based architecture to detect the structural changes, which are modeled via inflection points. And these are then coupled with a flexible DTW framework to generate the fine alignments. We employ standard convolutions as well as dilated convolutions and experiment with varying dilation rates. And our goal is to incorporate short as well as long-term context, which is rendered possible by using dilation. So what we mean by dilation is like inflating the kernel by introducing holes in the convolutional kernel. So an example on the right where the dilation rate is 2. So basically for a dilation rate of D, there are D-1 holes introduced in the kernel. And so the effective receptive field is increased exponentially. So this is the architecture of our model. As you can see, this is the best performing architecture with progressively increasing the dilation rates. So in the first layer, we use a standard convolution, and the other 2 layers, we use 2 dilated convolution and a 3 dilated convolution. And then in the output, we want to predict the inflection points, sequence of inflection points, which basically encode the jump locations. These are the equations corresponding to the dilated convolution operation, where D is the dilation rate. And this is the M dash is the new effective receptive field. And the effective receptive field can increase exponentially with dilated convolutions, as opposed to linearly with standard convolutions. So our networks basically operate on the cross similarity matrix, and they predict the XY coordinates of the inflection points. These inflection points are passed through a flexible DTW framework. Basically, we extend the set of predecessor cells for the jump locations. And now we'll talk about the experimental setup for our experiments. So since there is a lack of annotated data marked for repeats and jumps accurately at the frame level, we generated synthetic samples containing jumps and repeats. And for this, we use the audio from the MSMD dataset. And for each audio, we basically use it 5 times, one without any jumps and repeats, and 4 times with a different number of jumps and repeats. So basically, each performance score pair is utilized 5 times, and then we have a total of 2625 pairs. And additionally, we also use a small amount of hand annotated data, which we procured from Tido, UK. This is 150 audio pairs, and we also report results on models trained just using synthetic data, and also those trained using synthetic as well as real data. So as I said, the model inputs are the cross similarity matrices, and we train our models using the L2 regression loss, and we test them on the publicly available Mazurka dataset and also a private Tido dataset. For the private dataset is used to exactly measure the improvements on pieces containing structural deviations and those which do not contain any structural deviations. So now we'll report the alignment accuracy. So this is our model nomenclature. DCNN basically stands for dilated convolutional neural network, and M and N are the dilation rates at the second and third layer. And this is basically the alignment accuracy in percentage, where each value denotes the percentage of beats aligned correctly within the corresponding time durations of 25 milliseconds, 50, 100, and 200 milliseconds respectively. So these are overall results on the Mazurka dataset. And as we can see, that our models perform better than match by 4 to 6%, and better than jump DTW and Needleman-Wunsch time warping by 1 to 4%. And our model trained exclusively on synthetic data also yields better alignment accuracy than jump DTW, which actually requires manually annotated block boundaries. So this shows the applicability of our model in real world scenarios where there is a lack of annotated data. So also, in addition to this overall accuracy, we also want to analyze specific improvements for structurally different pieces. And we want to make sure it doesn't impair the alignment accuracy for pieces where there are no deviations. So we performed experiments on subsets of the Tido data set with containing structural differences and those containing not. And we report them in the next slide. So as you can see, our models show an increase of 2 to 5% in alignment accuracy over jump DTW and NWTW for the test set containing structural differences, and an increase of 1 to 3% on the test set not containing structural differences. And if we compare with match, actually the increase on the subset with structural differences is huge, like it's 9 to 10%. And then there is also an increase of 1 to 2% on the subset without structural differences. So basically, our method doesn't impair the alignment for non-structural so-called pieces. And at the same time, it improves the alignment for pieces with structural differences. So we also did a qualitative assessment of the alignment plots. And on manual inspection, we found that the progressively dilated models could capture long-term context as well. And we report some qualitative results here. So as you can see, while jump DTW struggles with deviations from the score, which are not mentioned in the score, Needleman-Wunsch struggles with cases containing both forward and backward jumps, for example, in this case. And this could be attributed to the weighting mechanism of Needleman-Wunsch algorithm. And in our case, we can see that we can capture both forward jumps as well as backward jumps. And while we can capture long-term context, the one case where our model struggles is when there are multiple deviations in a short time span. For example, in this case, in the second example. So then we move forward to discussing the results. As I said, these are the increase in accuracy over jump DTW and Needleman-Wunsch, and also match. And since our model can deal with just synthetic data, and it doesn't require a lot of annotated data, so it's actually quite applicable in real world scenarios. And also it does not require the jump locations a priori. So that's the advantage. Like, we do not require the manually labeled block boundaries. And we can also deal with the deviations from the structure in both the directions, forward as well as backward. So also our model can be also used with other feature representations, such as learned frame similarities or multimodal embeddings, in case we want to use raw sheet music, raw images. And it can also be used by non-DTW based methods, like the inflection points predicted by our model can be further employed by other approaches, for instance, using the score following approach by Doffer based on reinforcement learning. So to sum up, we demonstrate that progressively dilated CNNs are effective at structure-aware alignment. And we show a noticeable improvement in structural alignment, and also a slight improvement in non-structural alignment, so to say. And our methods can be used with raw images as well, by using different features, representations, and also by other approaches which are not DTW based. So some limitations of our model are the handling of trills and cadenzas, and we would like to address them in the future. And we also want to experiment with using parallel dilation and then merging the learned features. So that's about it. And thank you for your attention. I'm open to any questions. Thank you.